Welcome to the Ultralight Airplane Workshop. In this video, we're going to talk about choosing materials to use in building our ultralight airplane, and we're going to talk about some ways to use those materials in the structure. I have a message for my patrons. Earlier this month, I released a video numbered 10A, and you may have noticed that this video is numbered 10A. I decided to redo that 10A that you saw. So this 10A is going to be a little bit different. The one you saw, I'm going to redo. I decided to take it a little bit different direction, and that will be numbered 10B, and I'll talk more about that at the end of this video. As is tradition with this video series, let's cover what we talked about in the last video. Now, last video was covering propulsion, and we wanted to figure out how much horsepower do we need in order to go to our maximum level flight cruise speed. Now remember, we're limited to 55 knots. We calculated that we would have 52 pounds of drag at 55 knots. And we calculated two different ways how much horsepower we would need in order to get 52 pounds of thrust. And we came up with 20 horsepower and 22 horsepower. And that was using an Ultra Prop 1 with 10-degree pitch blocks. And also, let's talk about Dan's book. We're using Dan's book to help us figure out the design here for the UWS-4 Ultralight Airplane. And so far, I've been really impressed with Dan's book. He did a really good job of simplifying how to do the aerodynamic design of our airplane. If you might be interested in Dan's book, there's a link down in the description for this video that will take you to a page on the Ultralight Airplane Design website where I have a list of books that I like to use. And one of those will be Dan's book. If you click on that, it'll take you to an Amazon link where you can buy that book if you want to. If you do buy it using that link, the Ultralight Airplane Workshop will get a very small cut of the proceeds. We are continuing with Chapter 7 of Dan's book. We are now in the third section of that chapter. And by the way, that chapter is called Analyze It. And we are going to be working on preliminary structural sizing. That's on page 97. In this video, I'm going to cover or summarize some of what Dan talks about in this section. And then I'm going to take it a little bit further. But I'm not going to cover everything that Dan talked about in this section. I'm actually going to make this video into multiple parts. I already talked about having an A part and then a B part. I'll probably even have a C part. We'll see. And one thing that Dan mentions early on is structural sizing should not, or maybe even cannot be simplified. And that's mainly because there's so many different variables involved. For example, you can have a variety of different building materials. And here I've listed a few. We can have wood, aluminum, a steel tubing with fabric covering. You can have composites, which can be fiberglass or carbon fiber, and that construction can be either solid or sandwich type. And wood can be fabric covered or all wood. So you have quite different combinations of possible building materials here. And then you also have the construction techniques. There are a number of different construction techniques, and there are a number of different kinds of structures you can build. You can build truss, monocoque, semi-monocoque, a number of different kinds. And so you add all these variables together, and it's really difficult to come up with a simplified book for covering structural sizing. Now, I've talked about using aluminum for quite a bit of this airplane here, so that's going to bring about some issues. And that issue is minimum gauge and gauge steps in the extruded parts of aluminum that we can buy. For example, on aluminum sheet, generally the thinnest sheet you can get is 16 thousandths of an inch. And then the next step up would be 20 thousandths. Next step from that is 25 thousandths, 30, 40, and it keeps increasing in steps. Another example is round tubing thickness. Generally, the thinnest you can get is 35 thousandths, and then 49, 58, 65, and it keeps increasing. And angle extruded thickness, same thing. Generally, the thinnest you're going to find there is about 63 thousandths, and then 1/8 of an inch, 3/16, 1/4 of an inch, and so on. And the reason this minimum gauge can be an issue is, let's say we do a calculation for some aluminum angle, and we decide a thickness of maybe 50 thousandths would work good for us. But the minimum we can get is 63. That means we're going to have to carry around extra weight. And with ultralight airplanes, we will probably encounter this a lot. Now, you might get lucky and you might be able to drill lightning holes in various places in your angle and reduce some weight. But this minimum gauge is going to be an issue for us. Now, the gauge step can also be a very similar issue. We might do a calculation that says we need, let's say 100 thousandths thick angle. Well, we got a choice of 63, that's too small. or we have a choice of 1/8, and that's too big. So again, we might have to carry around extra weight just because we can't get a 100 thousandths thick angle. But again, we might be able to drill some holes, some lightning holes in and save some weight. As I've said before in previous videos, I want the bulk of the structure of the UWS-4 Ultralight to be aluminum. And by the way, if you haven't seen the previous videos on the UWS-4 design, I'll put a link up here in the upper right-hand corner that you can go to, and it will give you a playlist for all the videos I've made so far on the UWS-4. There are some exceptions to using aluminum on the airframe. One of those is the control surfaces. I had intended to make an aluminum framework and cover it with fabric to try to save some weight. But for the most part, I was going to have all the skins be aluminum sheet. And in our case, the minimum gauge we can use for sheet is 16 thousandths. And that's for both 6061 aluminum and 2024 aluminum. So even if structurally we could get by with thinner aluminum, we're stuck with 16 thousandths. Now another exception to using aluminum was my plan to use a steel tube truss for the fuselage and then cover it either with aluminum or fabric or possibly a fiberglass shell. I hadn't decided that yet. And then I was going to make the landing gear out of steel tubing. Well, I ran across something in Dan's book that I had not seen before, and Dan says that a steel and fabric truss framework weighs 80% more than aluminum truss framework would. So that's making me second guess what I'm going to use for the fuselage of the airplane. Now, Dan recommended another book to do for structural analysis, and that is Tom Rhodes' book, Stress Without Tears. And he also says steel tubing truss is heavier than aluminum tubing truss. Well, that prompted me to go off and do a little bit of analysis. In particular, tubing in compression, with different modulus of elasticity. Aluminum and steel have different stiffness, the modulus of elasticity. And it turned out they're right. At least in compression, you can make aluminum tubes that are much lighter than steel tubes, but still perform the same. And since a significant portion of a truss is in compression with aluminum, you're going to save weight. And by the way, if you'd like to see some of the analysis I did, I started a new video series. And this series is going to be on structural analysis, similar to the Aero terminology video series that I've done. And I've made a video for that series. You'll be able to find a link to it up here in the upper right-hand corner. You can click on that link, and it'll take you to a video where I did compression analysis on tubes, particularly steel and aluminum tubes. So what are my options for aluminum fuselage now? So I could stick with the truss style fuselage, or since it's aluminum's a little bit easier to work with, I could switch over to a monocoque or a semi-monocoque fuselage. Probably not a monocoque. There's going to be too many hard points in this fuselage that I want to deal with, so it'd probably have to be a semi-monocoque. And speaking of attach points, for example, the wing, it's going to attach at 3 hard points on the fuselage and the wing, 2 on the main spar, 1 on the rear spar. Now, if I switch to a monocoque, there's going to be a lot of sheet, aluminum sheet covering this thing. So impalement of sheet isn't quite as big an issue, but in that case, you have an issue of aluminum tearing in a crash and then getting cut pretty badly by torn aluminum edges. So I'm going to have to give this some more thought. The one thing I probably will stick with as far as using steel tubing, and that's going to be the engine mount. That engine mount takes a tremendous amount of vibration. And steel tubing doesn't have a work hardening issue nearly as badly as aluminum does. Aluminum can work harden if you violently shake it a lot, which you're going to get with this engine. Now, I'm not saying you can't design it. You can design an aluminum tubing engine mount, but there's a better reason for having a steel tubing engine mount, and that's fire in the engine compartment. If you have a fire there in the engine compartment, your steel tubing engine mount is going to last a lot longer. It's going to retain its structural integrity longer than an aluminum engine mount would, since an aluminum engine mount will melt at a much lower temperature than the steel would. Let's talk about some more of the aluminum structure I want to do on the airplane. Let's work on the wing here. So for the main part of the wing, that would be the nose and between the 2 spars, I'm going to use aluminum skin, and that aluminum skin will be used to take up the torsion load on the wing. That wing is going to want to twist as we're flying. It's going to want to twist nose down, and the skin will take up that twist to keep the wing from twisting. Now, another thing that skin will do is take care of handling drag on the wing, so the wingtip won't move backward. The skin will help take care of that. If we didn't do that, we'd have to put something called drag bracing in the wing, which could be tubes or wires, but the skin will take care of that for us. So the skin will be doing two things. It'll be taking care of the torque, and it'll be taking care of the drag load. So that's kind of nice. And as I mentioned before, the minimum thickness we'll be able to use on that skin is 16 thousandths aluminum. Now the spar I'm thinking about using is going to be inspired by the spar that was used on the Ultra Cruiser by Maury Himmel. So it'll be a built-up spar instead of an extruded spar. An extruded spar would be nice, but I can't find any that have the dimensions I want, but is also as light as I want. So I'll probably have to build it up. And I'll show you a little bit more about that here in a moment. So it's basically going to be extruded aluminum angle for the spar caps, and then it'll be aluminum sheet for the shear web, and then I'll have to put stiffeners in a few places to help stiffen up that shear web since it's going to be a pretty thin sheet. And then on the outer portions of the wing where I don't need full height shear web, where I can remove some of the material, I'll have to think about how I'm going to do those lightning holes. Typically in the past, you just use a round cutter and cut round holes to remove extra, but I'm going to think of maybe doing that a little bit different. And we'll talk a little more about that here in just a moment. And then ribs, again, I'm going to use formed sheet aluminum for that. So I'll make a rib form and bend the aluminum sheet over those forms to make my ribs. And again, I'm going to think about how I'm going to do lightning holes in that a little bit differently than is typical. The outer wing panels will attach to the center wing panel using 3 bolts, 2 on the main spar, and then 1 on the rear spar. Let's take a look about what I just talked about here. Now I've used FreeCAD to draw up something to give you an idea of what I'm thinking about for this wing center section spar, the main spar. So as I said, I'm thinking of building it up. Spar cap up here would be aluminum angle, and the size of that angle is yet to be determined. I'm going to have to do some calculations on that. Let's give ourselves an end view here. So you can kind of see that this is aluminum angle here, although I've removed a little bit of a section here and a section down here. Now this is where we would attach to the outer wing panel, but the majority of the load would be carried up here in this portion of the angle and this portion of this lower angle here. And then we would use aluminum sheet here in the web area. The web would be riveted to these 2 angles out here on the vertical part of these angles. Let's look at a front back view again. And as I said, in places we'll be able to remove some material from this web. And so now I'm thinking, instead of doing the typical circular cutouts for lightning holes, I'm thinking of doing more of a truss shape. So in these areas, right here in these vertical areas, that's where ribs would attach or stiffeners. And then we would do the typical flanging of these cutouts here. Now this center section, it's likely that I won't be removing a material for lightning. I'll probably need the full thickness, I don't know yet. But on the outer panels, I won't need as much web because there isn't as much shear load being carried along the spar out on the wing tips. So out there, I will be cutting some lightning holes. And then again out here where we do the attachment, so there will be a hole drilled here, and a hole drilled here, and something very similar on the outer panel where I'll attach the outer panels here on this main rib. So this is just kind of to give you an idea of what I'm thinking about for the spar on the wing. Now this is what I'm thinking about for the nose ribs. Again, really I'm only showing you the lightning holes here. So this is how I would probably cut out the lightning holes. And again, these would all be flanged in here. This would act like a truss here, here, and here. And then of course I would have a flange here on the back edge that would rivet to the webbing of the main spar. And that would have flanges along this top, along the bottom. And that would allow the skin to be riveted to the ribs. And then something similar would be done for the main part of the rib. Let's take a quick look at that. So here's the main rib. So up here, there'll be a flange. That would also rivet to the web of the spar. And again, we have these cutouts to make a truss system for the rib instead of the standard round holes. And there'd be flanges on all these edges. And there'd be a flange on the top and the bottom. Again, that's for the skin to rivet to. And there would be a flange on this back edge that would rivet to the rear spar. Let's briefly talk about what I'm thinking about for the rear spar. Now here I just have a primitive sketch I haven't filled it in yet, so it's going to be a little bit harder to see what I'm talking about. But here would be the skin. Up in here would be that main spar we just looked at. This right here would be the rear spar, and again, it would be made up of just sheet. There shouldn't be any need to do an extrusion for that. So it'll be folded over or flanged up here, riveted to the skin here, and again down here. So it'd be something like about a 3/4 of an inch length down here. And by the way, this height is about 6 inches here. Oh, and the main spar is about 11 inches high. So the wing control surfaces, again, probably an aluminum framework with fabric covering. Ailerons hinged at the top of the control surfaces. And then we'll have a little bit of a nose overhang to create drag when we're deflecting the aileron up. That counters our adverse yaw. Flaps hinged at the bottom of the airfoil surface. Try to have something that's like a slotted flaps when the flaps are deployed. And so we might get some slotted flap effect. That's the hope anyway. Let's talk a little bit more about what's going on here. Now this is actually what I'm thinking about for the flap, although it'll probably change. Now, the flap would be hinged right down in this area using piano hinges, at least 2 spots, and well, for the center section it'll definitely be 3 spots. For the outer panels I'm thinking 2 spots. Now since it's hinged out here and we've got about 3 inches of aluminum here, we have to have some way to stiffen that up a little bit. This is a cross section. This would be also made of sheet aluminum, very similar to this rear spar, but it will probably be much lighter construction than spar. The only purpose for it is to support this area where the one flange of the piano hinge is going to be riveted. The other flange would be riveted here where we have this overlap for the skins. For whatever I'm going to do for the framework for this flap, I haven't decided all of that yet. But any ribs I would put here in this flap would be very similar to what we've been looking at. Lightning hole. And then I probably don't need a truss framework back in this open area back in here. I have yet to figure that out. And since we're talking about this flap back here, I have another thing to look at. Well, here's the sketcher view of the flap. This point right in here, I don't know if you can see it, I'm making it flash yellow a little bit. That's a 75% chord of the wing, and that's where I want to put my hinges for both the flaps and the ailerons. So the flap hinge will be right down here at this bottom where I just talked about, down here at the 75% point. For the ailerons, it's going to be just under the skin right here at the top, although the aileron will have a different shape. We'll talk about that here in a moment. I'm going to make this flap so that it is kind of a slotted flap. It probably won't be that effective, but I'm going to try to take advantage of some of the qualities of a slotted flap. So that's why I made this top section up here the way it is. And let's talk a little bit about that. Now the hinge is not going to be full span. It's only going to be maybe 6 inches at each end of the flap. Rest of the flap is going to be shaped a little bit different. Instead of the skin down here on the bottom extending all the way out here to the hinge, it's actually going to stop right here at the back edge of the rear spar. But then the bottom edge of the flap will come right up to it and there'll be a little gap right here. So the shape of the aileron will be a little bit different away from the hinge. But the top side of the aileron will be the same, the full length. You might be able to see this line here, this construction line. If you think about an arc centered down here at the hinge, then that arc would come back here like this. We can see the front edge of the aileron is quite a bit down below that. In fact, you can see that it's about 1/8 of an inch gap here, but then it sharply curtails down and it's almost a 1/2 inch gap here. And that's about a 40-degree arc from the gap opening to the front edge of the aileron. That means when I deflect this aileron down 40 degrees, this area here will be up at this gap here. Now what will happen down here at the bottom is that this gap will open up as the flap is deflected down. So it'll be a large opening here. And there's going to be a large opening here all the way up to this gap, where it'll only be a 1/2 inch opening. So there's going to be high pressure down here on this bottom. That high pressure air is going to want to be going where this low pressure is on top. So that air will come around this admittedly very sharp corner, up through the gap that'll be in here, and then shoot out the top in a stream, a little jet of air. What that should do is help energize the rest of this air coming over the wing and keep it attached to the flap as it's going to curve around this deflected flap. I hope that made sense. I decided not to make an animation for this just because it would take so long. But as we get a little further along, I'll make some animations so this makes more sense. Now let's briefly look at the aileron. It's going to be similar. So once again, here's the rear spar. And by the way, the rear spar is going to be identical for the flaps and the aileron. It's going to be continuous along both the outer panels and on the center panel. And that just makes construction a little bit easier. When your rear spars line up for each section, it's much easier to attach them. Again, there will be some stiffeners here to handle this, about 2.5 inches of aluminum skin coming out here, because there's going to be a hinge here for the aileron. So the flaps hinge down about here for the flaps, up here on the top for the aileron. Here is the front face of the aileron. Now I didn't bother drawing ribs out here. I may not even put ribs into these ailerons if I can get by with it. I just don't know yet. I'll probably need ribs. Here is the gap, the opening for the aileron, and I've drawn here 25 degrees going forward and 30 degrees going back here. You can ignore this line right here. That was just to help figure out where this rear spar needed to go. So that means when I deflect the ailerons up, I'm going to be able to handle at least up to 30 degrees of deflection. Now I drew this arc here to show where this leading edge of the aileron is going to move as we swing the ailerons up. And you can see this leading edge is going to come down into the airstream as we start moving the ailerons up. Now I did that to try to create drag on the side of the ailerons that are going up. That's trying to help deal with adverse yaw, because the side of the ailerons going down, just because we're going down and increasing lift, we're going to get induced drag. This induced lift here, the drag due to that, is going to make the airplane try to yaw the wrong direction when we're trying to roll. And then this leading edge, when we're going down, will come up into this empty space here that I have. At least that's the plan now. This could all change. So let's move on to the V-tail stabilizers. So for the stabilizers, at least for the skins, I'm thinking very similar to the wing. We'll use skins of aluminum 16,000ths gauge. Now, if I can get away with it, I'm only going to put ribs at the dihedral changes. So here's our V-tail. Let's zoom in here a little bit. So the dihedral changes, we probably have one down here at the boom. Here's a dihedral change, so there'll be a rib here, and then identical on the other side. I'm hoping that's all the ribs I need. We'll find out here when we do some analysis. And then we're going to have hard points attaching the V-tail to the booms. And again, I'll probably have 3 attachment points, one near the leading edge of the V-tail on each boom, and then 2 probably back at the spar of the V-tail on the booms. Now the rotovators on our V-tail will be somewhat similar to the wing. So again, aluminum framework with fabric covering, but instead of having a piano hinge, I will probably have a plane hinge, and it'll be centered at the airfoil thickness instead of on an upper or lower surface. So let's go talk about that just a little bit. Now here's a really crude drawing of what I'm going to do on the V-tail. So again, here's the stabilizer part of the V-tail. There'll be a spar back here right before we get back here to the control surface. I don't think there'll be any need for a spar up front. And again, I'm basing this idea on what the Ultra Cruiser did for its horizontal tail, very similar to this. And then on the control surface back here, so there'll be a plain hinge, kind of a bolt hinge right back in this area here. I'm going to have a little bit of overhang here. Let me see if I can get the drawing up here to show the angles and circles in here. So here you can see the construction circles I used in making this overhang. So right here's where the hinge would be. As this nose starts coming up, this back end deflecting down, you can see the circle that it's going to travel. Now, it won't go up past this spot right here. But what will happen, because of this curvature here, this curvature will come up into this free stream air and then come down and meet up with this surface back here. This would be the circle that a plane flap would be. You can see I've extended the nose quite a bit out here. So about a third again of what would be for the plane flap. So as the rear is deflected down, the nose comes up, this curved part is going to come up into the free stream and re-energize it and help it stay attached to the control surface as it comes around over the top and then down the backside. Now, a good question would be, why aren't I going to hinge it at the top or the bottom like I did on the wing? Well, if we were doing a horizontal tail, at least on the elevator, that would probably be fine to do. But on the V-tail, that could give us a problem. Let's talk about that real quick. So on the V-tail, let's say we hinged it on the top surface. And let's say we let the control surface deflect the same amount up and down. Let's just say arbitrarily 25 degrees. So if it's hinged on the top and we deflect it up 25 degrees, there's going to be far more surface area being exposed to wind than if we deflect it down at 25 degrees. Since it's hinged at the top, this stabilizer is going to block a lot of that control surface, whereas when it's above, nearly the entire control surface would be exposed. Well, that means when we deflect it up, it's going to push down more than we deflect it down. Well, when we apply rudder in one direction, one surface goes up, the other goes down. Well, since we've got more pressure pushing down than we have pushing up, that means that the airplane will pitch up when we apply rudder. Whether we do left rudder or right rudder, every time we did that, the nose would want to pitch up. If we hinged on the bottom side, the nose would want to pitch down when we applied rudder. Well, by using a plane hinge centered in the middle, we get rid of that problem. Let's move on to the booms. I think I'll do the booms in semi-monocoque. At least it'll be semi up near the wings. It might be a full monocoque back toward the tail, except possibly right where the V-tail is going to attach. Skin thickness, I don't know yet what it's going to be. I'm going to start with thinking at 16 thousandths, and then if I need to change the thickness at various portions, I'll go ahead and do that. The booms will attach the wings with 3 bolts, and the stabilizers will attach to the booms with 3 bolts. And there'll be some bulkheads along the way at various points in the boom. Okay, landing gear. We've already mentioned this a little bit. I'm still thinking of using welded steel tubing for that, and they'll be bolted to the spar roughly right where the booms will be bolted. That'll take care of the boom and the main landing gear at the same time. I won't use the same bolts, but reinforcement of the spar only has to be done in one area. That's kind of nice. And then on the tail gear, that'll be bolted to the boom. Well, that's pretty much what I wanted to talk about in this video. The materials I'm going to be using and the initial ideas that I want to use for the construction using the aluminum for the material. Now, there's a lot of ways we could have gone about doing this. And it's very likely that what I've shown in this video is going to change. I mean, we've already come up with having to change the cabin just because the steel would be too heavy compared to aluminum. And it's very likely that what I thought about for possibly doing lightning holes in the ribs isn't going to work. It could be I'll have to revert back to round holes. And I imagine there's going to be a lot of that along the way. Now, I'm sure a lot of you have suggestions of ways to do it differently that you've seen done on different airplanes. I'll certainly take those thoughts into account and investigate them. Now, if I choose not to take your suggestion, that doesn't mean it's a bad idea. And it's very possible in future videos, I'll actually go and explain why I chose my idea over another idea. Or it could be vice versa. There might be a good idea come along, and I said, hey, that's fantastic, I should do that instead. And I'll definitely include that in the video. Let's talk about what's going to be in the next video. Next video, we're going to explore the flight envelope for the airplane and basically trying to figure out mainly the load factors that we're going to experience on the airplane, or what we're going to design the airplane to handle, and the various speeds that those load factors will occur at. And we'll also cover safety factor. Now, this video is the one I talked about earlier on at the opening, talking about the Patreons getting a video that I'm probably not going to make public. I want to redo that video. There's nothing wrong with that first video, but I've decided to change direction and do it slightly differently. Well, guys, that's it for this video. Thanks for watching. Until next time.